In this video, I will be talking to you about using one of the building blocks, or the basic building blocks of calculus, the limit, to establish a very critical concept in the use of differential calculus, that being the idea of using the limit to use the secant line, or the slope of the secant line, to approximate the slope of the tangent line. To do so, I have a sketch here, a geometry sketch pad, and what I've graphed for you is a curve. F of x equals 0.5, or 1/2 x squared. That's this green curve right here, this parabola. I've also created this line here containing the points D and B, intersecting the curve at 2 points, which I will call a secant line. The other line I have, this black line, I will call a tangent line. Now, some might say it's a tangent line because it intersects the curve at 1 point. Now, in all honesty, I could draw a line like this through point B that intersects it at 1 point. That does not make it a tangent line. So the mere intersection at a point does not make it a tangent line. What does is using a concept known as local linearity. What that basically means is when you zoom in on a point, I'll choose this point B right here, which I'll call the point of tangency. If you zoom in on that point on the curve, what it appears to do is the curve appears to be a straight line whose slope would match up with that same slope as this line here, which I call a tangent line. So let's begin. I'm going to start with my segment, or my line DB here, and what I've done is on the sketch pad I have it marking the distance from D to B, or the length of this segment that's contained within the secant line, and right now I see that its distance, or its length, is about 3.51. I can also visually see that its slope here does not appear to match up with the slope here. For those of you more numeric rather than visual learners here, 0.34 does not equal 2. So what do I do? Well, the idea is to take this point D on the secant line and move it a little bit closer to point B, my point of tangency. As I do that, two things are going to occur. One, the length of DB, or the length between points D and B on the curve on my secant line here, it gets smaller. Likewise, my slope, 1.12, while still not equal to 2, is a lot closer to the slope of the tangent line than it was. So let us continue. Move D a little closer to B. DB gets a little smaller. Slope of the secant line gets a little bit closer to the tangent line. So the question is, how close can I get? Basically, I want to get so close to point B that the distance between it, or between the 2 points, is approximately 0. Or I want the limit as my x coordinate from D approaches my value of the x coordinate of B. As that distance between the 2 points approaches 0, the slope of my secant line approaches the slope of the tangent line. Now, I did that in this particular sketch using a left-handed limit, or a left-sided limit, meaning my point B started on the left side of B and moved closer and closer and closer to B. I could have also done the same thing using a right-handed limit. In this case, my point D is on the right side of B. And again, you notice the distance of DB, rather large, and also the slope 3 not the same as the slope of 2 on my tangent line. As D moves closer to the point B again, this being the right-handed limit, my point D is on the right-handed side, you'll notice the length, or the distance between DB, getting smaller. As that distance gets smaller, the slope of my secant becomes closer in value to that of my tangent, And as those two distances approach 0, again you see how the slope of my secant does get extremely close to that of my tangent line. Okay, for those of you who are more visually oriented or visual learners, I hope that kind of helped you establish that relationship between how as the 2 points on the secant line get closer and closer together, that it approximates the tangent line. Here we're going to take a little bit more of an algebraic look at that same concept. To do so, I'm going to take just the basic quadratic parent function here, y equals x squared, and again I'm going to use secant lines to approximate the slope of the tangent line on the curve y equals x squared at the point x equals 2. So here's my parabola, here's my y equals x squared, my quadratic parent function. Again, I take a look at my secant line here in red, and then I've constructed a tangent line here in blue. My secant line containing 2 points on the curve, and again it doesn't take a Rhodes Scholar here to see that the slope of this red line and the slope of this blue line are not the same. So where do I go from here? Well, similar to what we showed in the sketch pad illustration, I'm going to take this point, which here is now at -1, 1, and gradually move it closer and closer to my point of tangency here at 2, 4. So if I start with my basic point here, -1, 1 and 2, 4, I calculate my slope to be 1. And again, if I take just a rise over run kind of look at the tangent line, up 1, 2, 3, 4 over 1, slope of my tangent line visually looks to be 4. The algebraic slope here we got from the secant line, not 4. So let's move this point closer to my point of tangency. So to approximate the slope, we need to choose a point closer. So what I did, or what I recommend you do is, well, I want to get really, really close to the point 2 without actually equaling 2, but being extremely close. 1.999 is pretty close. Now, I don't just pick this point out of thin air. Remember, these points are contained on the function y equals x squared. So if you square your independent variable 1.999, or your independent quantity, I get this y. Now visually I see, hey, wait a minute, as this point 1.999 gets extremely close to 2, and notice it's smaller, so this is a limit as x approaches 2 from the left. You'll notice by use of my difference quotient here that my delta y over delta x gets really, really close to 4, which we said appears to be my rise over run of the tangent line. Now again, you can do this with points not only on the left side of 2, but also on the right. So that's what we're going to show in the next illustration. Instead of picking 1.999, which is close to 2 from the left side, we're going to do the same thing with a point on the right side. So we're going to deal with a right-handed limit when x is 2.001, something slightly larger than 2, but yet approaches it. Again, with the aid of our graph, it appears as if the slope of the secant and the tangent overlap, that they're basically the same thing. Let's check algebraically. So if I take the point on the right, 2.001, really, really close to 2, I get a y value very, very close to the y value here of 4 from my point of tangency. Again, using change in y over change in x, I get a slope of a secant extremely close to the slope of my tangent. So the lesson learned here, you can do this as a limit from both the left side, numbers slightly less than your target value, and also the right side where you pick numbers extremely close but greater than your target value.